Welcome to the Biomedical History Lecture Series of the NIH Office of History. I am Alan Schechter, head of the Molecular Medicine branch, but was also a past acting director of the History Office, and I try to remain active in efforts to preserve and interpret biomedical history, especially that related to the NIH. I'm very pleased today to be able to introduce Professor Nathaniel Comfort of the Institute of the History of Medicine at Johns Hopkins University. Dr. Comfort will talk today about a topic that is a fundamental aspect of his very important 2014 book on the history of medical genetics. The book was entitled The Science of Human Perfection, How Genes Became the Heart of American Medicine. And the emphasis today will be on what he calls the enduring dream of controlling human heredity. Dr. Comfort received his Ph.D. degree in history from the University of the State of New York at Stony Brook in 1997, while also working at the Cold Spring Harbor Laboratory nearby. And he was on the faculty of the George Washington University from 1997 to 2003, when he went to the Johns Hopkins University. He's equally well known with the book on medical genetics that I mentioned for his 2003 book published by Harvard University Press on Barbara McClintock and her early studies of movable genetic elements, which he called the studies of genetic control. I should add that his talk today is a continuation of a series on biomedical history that was started earlier this year by Chris Wanjak, the acting director of the History Office, Chris Donahue, the historian of the Genome Institute, Jeff Resnick of the National Library, and myself and several others. We would very much appreciate any comments you and the audience have about this series, especially suggestions for other lecturers during the next year or two. But now let us hear Dr. Comfort's lecture entitled A Galaxy of Genius, ? The Enduring Dream of Controlling Human Heredity. Nathaniel, welcome to the NIH, and we thank you for sharing this hour with us.
Thank you so much, Alan. It is great to be here. I've given several talks at the NIH. I wish I could be there in person, but I have a long and warm relationship with the NIH and with the History Office. And I want to say thank you also to Chris Wanjak for making the invitation and making this all happen. So in 2015, an international summit held at the National Academy of Sciences in Washington, D.C., brought to the world's attention the recently developed gene editing technology known as CRISPR. If you believe the headlines, this DNA revolution will enable us to edit humanity. Supposedly, this new engineering power will permit a new eugenics in which designer babies are a matter of rational choice rather than chance and love. This will lead, Wired tells us, to the end of life as we know it. Even Jennifer Doudna has expressed fears of the possible implications of this Nazi-style master race and so forth. She often recalls a dream she had in which she had to explain CRISPR to Adolf Hitler. He had a pig face, she wrote, and I could only see him from behind, and he was taking notes, and he said, "I want to understand the uses and implications of this amazing technology." I woke up in a cold sweat. The most revolutionary thing about CRISPR may not be its biochemical power. Equally potent is the way it democratizes genetic engineering. So easy is it that DIY CRISPR kits go for a few $100 online. What could go wrong? The urge to improve our heredity runs very deep in our history. It captures the urge to organize society rationally, the drive for self-improvement, the quest for perfection. In the Republic, Plato's description of a perfectly logical society, Socrates reasons that when raising dogs and chickens, we naturally select only the best individuals to mate, so it should be with the human citizens as well. In the 18th century, Enlightenment thinkers in France and Germany had similar ideas. Convinced that the human race was degenerating, they drew up and discussed detailed concrete plans for female stud farms and other breeding programs. In the age of colonialism, the 18th and 19th centuries, the exploration seemed to Europeans to bear out the idea that Europeans were the evolutionary pinnacle of humanity. What do you know? Throughout the growing British Empire, explorers found peoples they found primitive, in quotes, seemingly stalled at an earlier stage of evolution. Thus, science provided immensely convenient support for racism, colonialism, slavery, imperialism. It's no accident that the British were leaders in anthropology, primatology, sociology, and human sciences at the time. American phrenologists picked up on hereditary improvement very early. The immensely popular Orson Squire Fowler wrote on human hereditary improvement as early as 1848. He talked about the law of heredity, which meant simply like begets like. Darwin's 1859 Origin of Species had included extensive observation and showed that within of enormous numbers of natural phenomena, and he showed that any given trait within a population had variants that would give individuals a slight edge in survival or reproduction. Any of those that affected survival and reproduction, he said, would tend to spread through a population, provided those variants were heritable. In 1871's Descent of Man, Darwin argued that humans were not exempt from this process of evolution. We were not the result of special creation. He argued we were simply one of the species of great apes. Darwin's contemporary, Herbert Spencer, argued that the path to human improvement was through natural selection. Let the poor, weak, and stupid kill themselves off. Spencer took a hard, laissez-faire line. He was against all forms of public safety net, public education, housing regulations, taxes of any kind. He believed in letting the strong survive and letting the weak perish, and so enabling the progress of the race or the species. Spencer, not Darwin, is actually the one who coined the famous phrase, survival of the fittest. So the term social Darwinism really ought to be social Spencerism. The ultimate result, he said, of shielding men from the effects of folly is to fill the world with fools. Others at the time worried that the human race would degenerate unless active measures were taken to counteract it. Often the concern over degeneration centered on the effects of modern industrial society. 2 years before the origin, the French prison director, Benedict Morel, thought that noxious influences could become heritable and create new subspecies of humans that expressed morbid deviations from the normal form. A few years later, in an 1865 essay called Hereditary Talent and Character, Darwin's half-cousin, Francis Galton, proposed that intelligence and other mental characteristics were just as heritable as physical traits. And he wrote that talent is transmitted by inheritance to a very remarkable degree. If so, he concluded, it ought to be possible to breed for it, as, say, dog breeders breed for herding or retrieving or pointing abilities. He imagined that if England's best and brightest could be persuaded to mate only with one another, there was no reason that a race of brilliant, successful, honorable men could not be produced. He did say that the brightest women should be selected, but he saw no place for them in the leadership of society. If a 20th part of the cost and effort that was spent on human improvement, he wrote, as was then spent on improvement of horses, what a galaxy of genius we might not create. Heredity and human improvement were major themes in Galton's writing over the rest of his long career. In 1883, he named this scheme eugenics for well-born. Galton was a pioneer also in statistics and biometry. He invented, for example, linear regression, which was derived from a study of human height. Galton was neither an important statistician who, oh, by the way, dabbled in eugenics, nor an evil eugenicist who, okay, fine, he did some statistical work. The two were intimately connected in his mind. Historical judgment needs to be nuanced enough to take this account of Galton's complexity. In the 1890s, a fan of Galton's named Caleb Saleeby made a key distinction that we still use often today. If you think of a bell curve distribution of any desirable trait, taking the 19th century views of IQ, health, whiteness, whatever a eugenicist might be interested in, eugenics tries to push the curve to the right. And there are two ways of doing that. One, through negative eugenics, would be to truncate the left-hand tail. Positive eugenics would be stretching out the right-hand tail, okay? Either one of those moves the mean to the right, okay? And increases the frequency or the quality of that particular trait, whatever it is, okay? Anything that moved the mean in the other direction was considered dysgenic. There we go. Eugenics didn't catch on socially in England as Galton had hoped, but in 1909, he did endow a Galton laboratory and a Galton professorship in eugenics at University College London. This was an intellectual school that developed the basic tools of modern statistics. Galton died later that year, ironically, childless. Eugenics did take off, however, in the US, particularly after 1900. Both scientific and social factors made human improvement much more than idle speculation. First, progressive era America was very different from Victorian England. Beginning in the 1890s, a groundswell of reform began to build, pushing back against the industrialist robber barons of the 19th century. Hundreds of reform movements emerged, from women's suffrage to temperance to public health to banking reform. Also, a spirit of collectivism flourished. Government seemed the only force powerful enough to stand up to those big industrialists. So Americans put their faith in bureaucracy, regulation, and legislation to solve social problems. It was also a time of remarkable advances in science and technology. The telegraph, the telephone, light bulb, powered flight, splitting the atom, radioactivity, and on and on. These contributed to a growing belief that science could solve any problem, including social problems. Whatever the problem was, as the character Mark Watney said in The Martian, you just need to science the shit out of it. This idea is known as scientism. So scientism is a quality that characterizes the progressive era very much. Okay? So in this frame, the rediscovery of the work of Gregor Mendel, whose pea breeding experiments in the mid-19th century revealed formulas for the patterns to predict the patterns of heredity, which were rediscovered in 1900. And in that frame of scientism, it seemed as though humans had cracked the very fundamentals of heredity. This self-direction of human evolution had never seemed so close at hand. Progressives were deeply concerned with human improvement, and genetics was an important tool in their striving for perfection. At the Panama Pacific International Exposition in San Francisco in 1915, eugenics was a major theme. Combined with euthenics or hygiene, eugenics could, they believed, just within a few centuries, practically wipe out intellectual disability and a score of other hereditary disorders, creating a race of human thoroughbreds such as the world has never seen. Note the horse trope appearing once again, and the long-term thinking. We rightly think of eugenics as being broadly sexist, classist, and racist, but we mustn't lose sight of the breadth of its appeal. My student, Aya Nuridin's dissertation on Black eugenics, completed last year, shows that African Americans also engage broadly with eugenic thought, including in medicine. A few years later, the African American president of the Pennsylvania State Medical, Dental, and Pharmaceutical Association echoed Jordan's statements about the importance of medicine, saying that preventive medicine is in the ascendancy today, marching boldly onto eugenics and the Superman via birth control. John A. Kenney, the General Secretary of the National Medical Association, the African American Medical Association created when when JAMA would not admit African Americans. He believed in eugenics in the form of marriage laws, limited reproduction, and improved morals. And he thought that these would slow the spread of diseases such as syphilis that led to, again, the idea of racial degeneration. Race theory, feminism, moralism, all drew upon eugenic rhetoric. Collective reform, scientism, and the use of government as an instrument of liberation were interpreted in many ways by different people with different political viewpoints. Margaret Sanger, the birth control reformer, saw many virtues in making contraception widely available, and one of them was the improvement of the race. Only when the parents of the world had control over their own reproductive faculties, she wrote, will we be able to improve humanity or even maintain civilization at its present level. Again, the idea of degeneration. Heredity is big problem, proclaimed this headline from 1926. Note here, the theme of comparing horse breeding to the breeding of humans. Even though intelligence was understood to be a spectrum with a bell curve distribution, progressive era eugenicists convinced themselves that there was clear evidence of a Mendelian gene that caused feeble-mindedness or subnormal intelligence. Feeble-mindedness, in turn, was thought to be the root of all antisocial behavior, crime, poverty, venereal disease, whatever. So drawing pedigrees and applying the newly introduced intelligence quotient test, the IQ test, psychologists, geneticists, criminologists, and others set out to stem degeneration. The improvement of the American race seemed to demand stern measures. And among those were sterilization laws. The US had begun passing eugenic marriage laws regulating who could marry whom before the turn of the century, and surgical sterilization was proposed as a eugenic measure. Indiana passed the first eugenic sterilization law in 1907. More such laws followed, always at the state level. The problem was they kept getting shot down as unconstitutional. So Harry Laughlin, the superintendent of the Eugenics Record Office at Cold Spring Harbor, New York, set out to draft a model sterilization law that would be constitutionally bulletproof. The test case for this was for the Virginia law, which was modeled on Laughlin's model law. The test case was the famous 1927 court decision, Buck v. Bell, in which the Virginia eugenic sterilization law was upheld in the case of the domestic Carrie Buck. The case is notorious in the stories of the elimination of the unfit, but often overlooked are the words of the Surgeon General, Claude C. Pierce, who saw this decision as a step toward a super race, if a feeble one, he said. The easiest path to human improvement has long been the reduction of numbers of, quote, defectives, i.e. negative eugenics, always defined as defined by contemporary society. Just important, though, was producing better and better babies. Fitter Families and Better Babies contests were popular attractions at state fairs in the 1920s and 30s. The contests helped spread awareness of public health and hygiene, and as well as allowing families to compete for eugenic fitness. Children were lined up and judged just like pumpkins. Compared to the genetics of other animals, though, human genetics was very slow off the ground. In 1956, one important reason was uncovered. They'd been miscounting the number of chromosomes. That year, Jo-Hin Chiu and Albert Levan found that humans have 46 rather than 48 chromosomes, as had been supposed for more than 30 years. This finding gave researchers hope once again that the self-direction of human evolution was just around the corner. At the same 1956 meeting where Chiu and Levan made their discovery known, the Congress president, Taga Kemp, stated confidently that the time was drawing near when man could control his own biological evolution. Molecular biology, too, gave great optimism about controlling our own evolution. Visionaries such as the biologist Joshua Lederberg speculated on a new molecular eugenics in the 1960s, in which one could potentially diagnose, then specify the actual DNA composition of the ideal man. But who decides what that composition looks like? Who's ideal? Visions of top-down social control remained strong until late in the century. His colleague, Severo Ochoa, one of the pioneers of DNA sequencing, Nobel laureate, he also wondered if one day we would soon be able to fix genes or even make them to order. Indeed, they would. In the late 1960s, the age of genetic engineering began. In 1969, Jim Shapiro, molecular biologist at MIT, and John Beckwith at Harvard announced they had isolated or cloned a bacterial gene. They understood the social implications of their science, but as 1960s Marxist leftists, they were concerned about the return of state-run heredity programs. They didn't want to see any kind of American-run, Nazi super race. So they took the unusual step of calling a press conference to warn people of the potential for the nefarious nefarious government-run eugenics. The New York Times called it a step in heredity control. But it wasn't the government. It was rather free enterprise that wound up pushing for genetic control. With the rise of medical genetics, heredity control moved into schools of medicine. Genetic engineers dreamed of using recombinant DNA technology to fix disease genes. The first attempts beginning in the 1970s were marked by hubris, arrogance, and the flouting of ethical norms, and scientists responsible were heavily censured. Legitimate gene therapy trials did not begin until 1990, the culmination of years of effort on part of the lead scientist, French Anderson, and others. And some saw these efforts at human improvement inevitable. Gene therapy, wrote the Financial Times, will inevitably lead to eugenics and an irreversible transformation of the human species. So this is a long-standing concern. Anderson was excited at the possibilities for gene therapy to permanently cure genetic disease, but he drew a hard line between therapy and enhancement. Gene therapy should only be used to treat disease, he said, not to enhance normal traits. And the memory of Nazi Germany remained vivid. Making a master race was right out. But the problem quickly became obvious. Where's the line between therapy and enhancement? Members of the deaf or little people communities might consider therapy to eliminate their disability as active harm. On the other hand, if someone one or more standard deviations below average height might request human growth hormone therapy on the grounds of, say, social stigma suffered by being short, loss of opportunities, maybe subtle ways that tall people tend to concentrate power. This is possible. Further, someone with small stature in the Netherlands might be a veritable giant in some parts of Asia. So these things are all relative. How do you decide? Gene therapy to permit survival of people with severe rare hereditary conditions came to be in a way dysgenic because of the in the case of Jesse Gelsinger, who had a rare disease that went into a gene therapy trial, and for reasons they didn't understand, he suffered a massive organ shutdown and died. So this was then in another trial in France, several girls in a gene therapy trial died when the gene meant to cure thalassemia was inserted into their genomes, but it inserted behind the wrong promoter and wound up causing leukemia. The NIH slapped a moratorium on gene therapy trials until we could get it straight. And gene therapy has come back slowly and never with the same degree of hype that it had in the 1990s. Reproductive technology also fueled dreams of human perfection. The development of the first cloned mammal, Dolly the sheep, in 1997 led to a flurry of cloning research, discussion, and emotional hand-wringing. It only took 4 years for another lab to clone a human embryo. Cloning and in vitro fertilization moved Time magazine to speculate about parents selecting for brains and beauty. Now, the ethical answers to these kinds of questions, or even scientific answers, might seem obvious today, but it's striking how similar the questions they asked at this time were to those raised by genetics throughout its history. In 2000, the Viscount Member of Parliament and science writer Matt Ridley named the elephant in the room. These technologies presaged a new eugenics. But instead of fretting over the E word, Ridley embraced it. This eugenics would be better than the old. Now we knew enough, he implied, to do it right. Do we? How do you ever know? Cloning spurred a great deal of bioethical reflection. Would cloning change human nature? Would a cloned person have the same rights as a naturally born person? Cloning embryos with benefits to science or technology or medicine was deemed therapeutic cloning, while cloning new babies was called reproductive cloning. Analogous to Anderson's line between therapy and enhancement. But ethicists and others quickly realized that, again, the boundary between the two was too hazy to enforce in any meaningful way. Since the turn of the 21st century, we've been living in the genome age. Much that the earlier visionaries predicted is indeed coming to pass. But as the last Holocaust survivors die off, the memory seems to be fading. The term eugenics is once again starting to be used by some researchers and bioethicists. It's becoming much less of a dirty word. In 2008, Cold Spring Harbor Laboratory reissued the arch eugenicist Charles Davenport's magnum opus, Heredity and Eugenics from 1912, prefacing it with reflections by contemporary genomics researchers. In the foreword to the book, Matt Ridley, you saw a moment ago, wrote that there's every difference between Davenport's Science of Human Improvement and that would be contained in the following pages. Davenport, he wrote, aimed to improve the race, even at the expense of individual happiness, while the new eugenics aimed for individual happiness with no thought to the future. A short-term, selfish neoliberal eugenics, then, was as opposed to the communitarian, foresight-driven eugenics of the progressive era. it's not entirely clear that this is a better eugenics. Imagining that science could be free of social or cultural influence, these authors in this book argued that controlling human evolution is fine in principle as long as the science is good and it's driven by self-interest. In the preface to the same volume, Ridley expressed this idea succinctly, Maynard Olson, a scientist, the well-known scientist of the Genome Project, said, here is the raw material for a real science of human perfection, okay? It's not that eugenics was wrong, they're saying, it was just that it was done wrong. And now we have the material to do it right. Anderson's strictures against gene therapy, against enhancement gene therapy, have since been relaxed. The possibility of personal genome sequencing and precision medicine fires the imagination again in these directions. Once again, techno-enthusiasts envision intelligently engineering our genomes to eliminate disease and birth defects, and perhaps even make us smarter or better at music or more generous. The bioethicist Julian Savulescu, one of the leading pro-enhancement voices in these days, even argues that we have a moral duty to genetically enhance our children. He calls this procreative beneficence. The CRISPR cheerleaders rightly point to the fact that our understanding of heredity and how traits are produced has increased dramatically over the last 150 years. The implicit assertion is that the genome is becoming comprehensible, manageable, manipulable. When CRISPR hit the headlines, critics immediately began sounding the alarms of eugenics once again. But proponents now had ready counterattacks. Just as we've seen, the same debate has played out many times. Okay? In late 2015, the National Academy of Sciences hosted the first International Gene Editing Summit, where we began. A consensus emerged that scientists should hit pause before proceeding with genomic engineering and germline gene editing. This recalled the moratorium placed on recombinant DNA technology in 1974 that was lifted at the 1975 conference at Asilomar in California. But the moratorium was broken before it was even made. A Chinese lab had already CRISPR'd human embryos. These embryos were non-viable and were never implanted, but the Chinese had demonstrated proof of concept. Their paper was accepted for publication less than 2 weeks after these cautionary articles appeared. It seemed like a shot across the bow. Sure enough, just before the second International Gene Editing Summit, 3 years later, held in Hong Kong, the Chinese scientist He Jiankui announced that he had, apparently successfully, inserted a gene that protects against HIV infection into 2 embryos that were implanted in the mother's womb, carried to term, and born. The first gene-edited babies were with us. He stunned the scientific world by making his announcement in a YouTube video. Capitalism drives this science in numerous and often subtle ways. Now, I want to end with a hopeful story, perhaps a story of how to do it right. For some years, the MIT researcher, Kevin Esvelt, has been developing an application of CRISPR called a gene drive. In essence, it's a way of getting organisms to do germline gene editing on themselves. Thus, once introduced into a population, the new gene is transmitted not in Mendelian ratios, but to nearly every one of an individual's offspring. For years, Esvelt has been testing models of gene drives in controlled wild habitats, islands that are being damaged by invasive species such as rats, or spreading disease such as mosquitoes and Lyme disease. Meaning that mosquitoes transmit the Lyme disease, not that mosquitoes are a disease. Aware that introducing CRISPR gene drives into the wild is highly risky, Esvelt has been conscientious about obtaining local buy-in to his projects. In 2017, he and colleagues published a paper in PLOS Biology on a program that they were running in New Zealand to eliminate the invasive rats that were destroying many of the fragile endemic species on New Zealand. But when the paper was published, immediate feedback from New Zealand scientists and indigenous leaders were sharply critical, particularly about Esveldt's lack of consultation with them on this paper. He had been working with them, he just didn't consult them on this paper. He then publicly apologized, pretty abjectly, really, and vowed to work even harder to ensure the transparency of his work and the full informed consent of any affected populations. He said that researchers should hold themselves morally accountable for all of the consequences of their work. And so this kind of work that has such potential to change society needs to be carried out in consultation with the people who are affected. Right? And that is hard. That's not just easy. And that means not just explaining to them, but actually being involved with them and listening to them. I'm sure Esveldt is no saint. I'm not holding him up as necessarily the model. I don't know him. And you have to have a lot of ego to even attempt to alter entire gene ecologies. And I'm not at all sure that releasing gene drives into the wild is a good thing under any circumstances. But Esveldt is attempting something interesting. Can you play God and maintain your humility? Can you admit your ignorance? Apologize for your mistakes? What are you doing? I hope so, because I can't see any forces, contemporary or historical, that would stop CRISPR and even gene drives from being attempted on humans. The impulse to control our own heredity, our own evolution, is too deep, too fixed in our nurture, and perhaps even our nature. As the future of human genetic engineering unrolls before us, we need to find ways to keep the process democratic without rejecting expertise. That'll mean public communication, listening as well as explaining, humility, maintaining humility, introspection on the consequences of your work, foresight, long-term thinking. Okay. Now, not entirely coincidentally, this is just what historians and other humanists do. Thank you for having me.
Alan, just a minute.
Yes.
Dr. Schechter, I will unmute you. Can
Fine.
you?
Good.
Okay. Oh, hello.
Hi. Let me begin by asking a question. Who do you, Nathaniel, who do you envision beginning the effort to have public communication and the other components that you feel are necessary to make enhancement or eugenics more acceptable than it has been over the past century?
Well, I think ultimately it has to come from scientists. I think there are a lot of people who can act as sort of midwives, humanists, bioethicists, and historians, sociologists of science, and others certainly can be part of that conversation, can be part of the communication as well. But scientists need to think that to be convinced that this is necessary. And it's hard. It takes work, it takes time, it slows down the research. There's a lot of reasons that scientists don't want to do this, right? If I were doing this kind of work, I would think, what a pain. How am I ever going to get anything done? But I think it's essential that this kind of care be taken when science is having, in genetics in particular, has the potential to have such a large impact on society.
Do you think the Asilomar model is appropriate? I was very interested in that, and as an editor of the journal Perspectives in Biology and Medicine, published a follow-up after 25 years on the Asilomar conference. But many of the people who wrote for that that issue of the journal thought that we were past that stage and scientists could not get together alone without the press and public representation now, and did not think the Asilomar model would work. And it's not clear to me what model would work in doing what you suggest.
Well, you can't keep out the press and the public. I mean, there were, of course, some press at the Asilomar meeting. But it was not open to the public. And I think these subjects need to be. And on a project by project basis, right? Not a general debate over the technology as a whole. I don't see that being terribly productive. I certainly think that it's interesting, and I think you could have scientific conferences that are introspective in that way. You might even have conferences of, professional conferences that bring scientists together with humanists and bioethicists. Could be very productive. But ultimately, I think what we need to do is inculcate a value, and perhaps it even needs to be woven into the funding mechanisms to encourage this kind of public consultation and debate and discussion in a genuine way of that's not just explaining to people what you want to do, but listening to concerns and even making adjustments to your protocols as necessary. I think those kinds of, so I think more of a, this might be controversial to say, but maybe a model closer to Cambridge, Massachusetts, and their recombinant DNA debates in 1976.
The city council discussion of recombinant DNA at Harvard and MIT that you're referring to.
Exactly, yeah.
Right. But let me go to some, we have a lot of questions, and we have a very strong audience and a good amount of time. Let me go to the first question I see on the chat. Ajay Pillai asks, we as a society might be able to put limits on the government, but we are unable to do that with private corporations, as is clear with privacy and the internet. Any thoughts on gene editing and the role of corporations?
That is a super question and a hard one. I don't know enough corporate law to make any kinds of concrete suggestions on that level. I do think that, I mean, you're absolutely right. The Asilomar model, was affected those who had public funding, and we are now in a world in which a large fraction of this research is privately funded. I'd be interested to get involved in a discussion about what we can do to create a value for doing this, to make it necessary for corporations to do this. I don't know, is it possible to stigmatize a corporation enough if they fail to do this? I'm thinking about Purdue Pharmaceuticals, which was heavily stigmatized for eventually, I mean, they did a lot of damage beforehand, but at least eventually there was enough public outcry that that they were heavily censured. Maybe that is a way to do it if there's enough of a public value for doing this, but we can't sweep it under the rug.
Chris Wanjak makes the comment that he wonders whether he would have been caught up in social Darwinism and the eugenic movement of the late 19th and early 20th century. And it looks like practically everybody in all levels of society in the United States and many in England, although not necessarily in the continental Europe, were there any groups that were against the eugenic movement? Was the church, for example, or W.E. Du Bois, or others specific? What was there a pushback? I have reason to believe that the Columbia anthropologist
Franz
Boas was against that type of action and was ascendant in his views until the First World War. But the nationalism that occurred throughout the United States with the First World War suppressed the attention paid to his views.
Absolutely, and that's I'm glad you brought that up. Belief in eugenics was very widespread in the progressive era, but there was pushback. Yes, there were opponents and people who were trying to resist it. And even from very early on, I think Boas began to get involved in these issues, if I'm not mistaken, around the mid-teens, late teens. And there had already been some criticism. And the criticism began to mount in the 1920s. And I think it did help push the eugenics down in popularity. And they also helped themselves torpedo their own reputation by becoming increasingly dogmatic and ideological. And so then scientists started opposing it as well. The question about the church is really interesting. There's a fantastic book by Terence Keel on Christianity and eugenics that has some very surprising things, and he talks about, so there were religious there was some religious opposition, but Keel argues also that the notion of humans as the chosen species, right? The closest animal species to God, helped promote a kind of eugenic ideology. So it's a really complicated and interesting book and issue. I'll be happy to send you the reference on that afterward if you're interested.
Thank you. Tonsei Raju makes the following comment. Thanks for doing this presentation. I am still struggling between appreciating scientific advances versus the risk of extreme applications of these. When blood transfusions were introduced or X-rays were invented, people were very scared of the negative implications of these advances. Likewise, even when printing was invented, there were concerns. The question of who is going to monitor these has always been with us. And we have to appreciate the double-edged sword nature of scientific progress from its very beginning.
Very well put. Very well put. Thank you for that. I absolutely agree. And I want to make sure that I don't come across as anti-science. I'm not anti-science in any way. I have 10 years of scientific training. I worked at as a PR guy for a scientific laboratory. And I have some of my best friends are scientists, right? So my goal is actually
Speak.
We can't hear you.
We can't hear you.
did I
Okay.
Just for a second. Yeah, you're good now, I think.
Okay. Fine now. Go
I
ahead.
don't know what happened there. Okay, some sort of little glitch here. My goal is to help, in any way I can, steer the science in positive directions. I do think that this that CRISPR and potentially even gene drives have real potential to help people and maybe even aid ecologies. And like Kevin Esveld, I just want to. I think it's possible to do right, and so we need to have these conversations to try to avoid the backside of that double-edged sword, and try to dull that side as much as we can, while the scientists are sharpening the positive side.
Thank you. We have an interesting question from Dr. Ian Miles, who thanks you for the talk and says you have nicely presented the debate on these issues when the ability for gene editing to make a strong impact is present. But I'm struck by the parallels to chasing the gene for in complex diseases that have not been shown to have a strong genetic component, such as allergy, autoimmunity, and many others. How do you think scientists and historians communicate how the eugenics-based ideals have perhaps distracted from efforts, i.e. non-genetic efforts, that could better impact disease? And I think he's referring to environmental changes as well as medications and many approaches to improving humans not based on genetics. Well, again, as implied in the title of your second book, not necessarily everything in medicine can be or should be based on genetic analyses.
That's a super question. Thank you very much for that. I left out, in the interest of time, discussion of genome-wide association studies and polygenic scores, which I'm super interested in. And I'm actually participating in a bioethics working group in which I talk with scientists who are doing this work, and we're trying to hash out ways in which the science can be done in a positive way. And I won't lie to you, I have disagreements with them. They have disagreements with me. There's a new book by Catherine Page Harden about called The Genetic Lottery, in which she argues for the use of polygenic scores for educational attainment in particular, which is, as she says, essentially today's proxy for IQ. It's not exactly, it means that for everybody, the years completed, years of school completed is educational attainment, and it's used as a proxy for IQ. And she argues that you need to have all the information available in order to create the best environments for children, and so we ought to be taking genetics into account. I disagree. I don't think genetics, polygenic scores, really tells us much of anything about educational environments. It only explains 3 or 4% of the variation in educational attainment, and a whole lot of things. We know that talking to your children is good, reading to them is good. We know that that wealthier schools that have more resources have kids who do better on standardized tests, go further in school, go on to have more years of college. And I absolutely agree with you that spending too much time thinking about genetics is time not spent on thinking about social inequalities that affect things like educational attainment, as well, of course, as health and all other aspects of society. So I think there are ways, I'm 100% in agreement that there are ways in which it might well be useful, and there are ways where it just, right now, I just don't think I don't see it ever becoming very useful.
Right. We have 4 minutes left, but we're getting robust questions. We've just gotten 9 more questions in the last minute or two. Let me go on. Helen Juliet asks, Muller's concerns regarding eugenics was the load that humans carry of mutations. With increasing nuclear buildup and chemicals in our environment, the issues of protecting people from adverse mutations remain. Where do mutations enter into the contemporary debate? And I do know to my own experience that 10 or 20 years ago, there was active studies of trying to estimate mutation load. I'm not sure those are still going on as much as when Oak Ridge and the University of Wisconsin investigators were trying to estimate the mutation load in people.
Helen, that's fantastic. Fantastic question. Thank you. And thank you, Alan, for that. Yes, I have to say I'm not aware of current studies looking at mutational load or genetic load, and I'm making a note to look that up and see what I can find on that. That's a super interesting question. I know that there have been questions, about mutation, increased cancer rates near toxic sites. The 1 in 9 group on Long Island concerned about radiation and mutation and breast cancer. So I know of studies looking at particular kinds of mutations or looking at mutations in particular environments, in exposure to toxic materials, basically. But the question, the larger question you raise about genetic load is super interesting. And I'm going to look that up. I'll get back to you on that.
I will send you the other questions as well afterwards. Perhaps we can do one more question before we end at our assigned 1 o'clock. Douglas Atkins says, doesn't seem likely that CRISPR usage or gene editing in general will not become widespread unless it benefits those who are already doing well by the current medical and social status quo. So he's skeptical that it would be used more widely than those who can afford it and have specific access to it in comparison to the population in general.
That's exactly right. That's exactly right. There's a long tradition in genetics of, and tradition, I mean, it's just been there for a long time, that when we ascribe aspects of human nature to the genes, it tends to, it need not, but it does tend to naturalize those differences and stratify populations, and that benefits, and and stratification always benefits those at the top and harms those at the bottom. So I think trying, doing everything we can to ensure transparency, and the kinds of things I listed at the end, real communication and so forth, are vital if we're going to do that. I share your skepticism, but I still, if I lose all hope, then there's no point in continuing. So thank you. That's spot on.
Okay, I think in view of the constraints we have pledged to follow up, we should end now. As I said, I will send you the questions, and I thank you very much for giving this very interesting presentation. I hope people will look, this will be video archived, so people in a day or two can look at this or share it with their colleagues. The previous lectures have been video archived, and we hope to have the next lecture in the second or third week of December, and we'll let people know about that shortly. But I want to thank you in particular and our audience. Good afternoon.
Well,
Yes,
thank you very much to everybody.